In this video, we're going to look at using partial fractions as a algebraic technique for integration. And before I look at partial fractions within an integral, let's just talk about what this algebraic strategy is and where it comes from. Let's consider these two rational expressions, 2 over x minus 3 plus 5 over x plus 1. What I'm going to do is add these two rational expressions together. In order to do that, I need to get a common denominator. So I'm going to multiply x plus 1 times the 2. And I'm going to multiply x minus 3 over here times the 5. And then put the whole thing over x minus 3 times x plus 1. I'm going to go ahead and distribute. There in the numerator, 2x plus 2 plus 5x minus 15. And on the bottom, if I multiply that out, x squared minus 2x minus 3. And then this simplifies down to 7x minus 13 over x squared minus 2x minus 3. Okay, you may be wondering, why are we doing this? This is just algebra 2. But what I'm doing is showing a process that we have seen before about how to add rational functions. What we want to do when we're integrating using partial fractions is we want to reverse this process. So, for example, if I start out and I want to integrate 7x minus 13 over x squared minus 2x minus 3, in this form, u sub is not a possibility because if I take the derivative of my denominator, it's not there in the numerator. There's really no other strategy here. But if I can decompose this rational expression and get it back to this form that I started with up here, then this is something that we can integrate. So that's what we want to determine how to do. So our first step is going to be to factor the denominator. And it's important to note here that this technique of using partial fractions only works when your denominator is factorable. So that denominator factors to x minus 3, x plus 1. So now what I'm going to do, if this factors like this, then I know that there is some fraction a over x minus 3, some term up here in the numerator, plus b over x plus 1 that has to equal this fraction here. And of course, we already know what it is because I started with that. But let's pretend we don't know what this is up here. I know that there's some numbers that would make this true because I have this denominator, x minus 3 times x plus 1. We could split it up into two fractions. So what I need to do is figure out what numbers go here so that if I added these together, I would end up with 7x minus 13. So what we're going to do is add these two rational expressions together, same way I did previously. I'm going to multiply the x plus 1 over here, a times x plus 1, plus b times x minus 3, and that's going to all be over x minus 3 times x plus 1. So here's what I want. I want this numerator to be equal to this numerator. Because if I can get these two things to be equal, if I can figure out what a and b are so that this expression equals this expression, then I can rewrite my original integral into something that I can integrate. So I'm going to say a times x plus 1 plus b times x minus 3. I want that to be equal to 7x minus 13. My denominators are equal. I need my numerators to be equal. So now we have to figure out what a and b are. And the way that we're going to do this, I will say it's a strategy. We're kind of using a shortcut on the strategy, which will always work. The shortcut will always work for problems that we will see in Calculus BC. If you are taking A squared I courses, or maybe you get into a second year of calculus in college, you'll see like a longer version of this process. But for now, we're just going to use the shortcut because it's always going to work for us. what I want to do, if I've got two things that I don't know, but only one equation, we've got to be pretty strategic. I want this equation to always be true for any x value. And so I'm going to pick some convenient x values. For example, if I let x equal positive 3, then I'm going to plug in positive 3 here. I'm going to get 4a plus, if I plug in positive 3 here, this becomes 0. And so I get plus 0 equal to, I should have plugged in the 3. 7, well, I'll just plug it in like that. So I chose 3 because it's going to make this term become 0. And now my only variable here is a, so I can solve for a. So 4a is equal to 21 minus 13, which is 8. And that means that a equals 2. So now I want to go back. I know that my a value is 2. I want to pick another convenient x that will zero out the a term so that I can solve for b. So let's let x equal negative 1. If x is negative 1, then negative 1 plus 1 is 0. So my first term becomes 0 plus negative 1 minus 3. That would be negative 4b. And that's going to be equal to 7 times negative 1 minus 13. So negative 4b equals negative 7 minus 13, which would be negative 20. And that means b would be equal to 5. So now I've solved for a and b. And we're going to plug these back in and rewrite our original rational expression. When you plug these back in, be really careful to make sure that you put them on top of the correct denominator. So my integral now is a, which I found to be 2 over x minus 3, plus b, which I found to be 5 over x plus 1 dx. And now these are in the form of a rational expression. We could use u substitution, but we're going to kind of do this in our heads because we're going to see this over and over again with partial fractions. This is how our integrals are going to end up. If I let my denominator be the u, my du is just 1. And so we don't really have to do the substitution. We can just say this is equal to 2 times the natural log of our u, which is x minus 3, because it would be like 2 over u. If u is x minus 3, then it's 2 times the natural log of the absolute value of u, which is x minus 3, plus 5 natural log absolute value x plus 1, plus c. All right, we're going to do one more example. Got the integral of 2 over x squared minus 4x minus 32. Now, if you look at this expression, it looks like expressions that previously we were using completing the square on. And so you might think, why wouldn't we just complete the square on this one and hopefully end up with an arctangent expression? I think that the partial fraction decomposition is maybe an easier process. Typically, our strategy is going to be whenever we see a quadratic in the denominator, now that we have this technique, the first thing we're going to do is check and see if this is factorable. And if it's factorable, then we're going to move ahead with the partial fractions. And in this case, this is factorable. This factors x and x, 8 and 4. I want it to be minus 8 and plus 4 so that I get that minus 4x in the middle. And then, of course, still have the 2 on top. So I've got my denominator factored. I know there are two fractions that should equal this expression, a over x minus 8 plus b over x plus 4. And I want this to be equal to 2 over x minus 8 times x plus 4. So I know that my denominators are already equal. I'm just going to find my new numerator over here, multiplying x plus 4 times a, and then multiplying x minus 8 times b. And I want this numerator to be equal to 2. I'm kind of skipping the step of rewriting the whole fraction because really what we need here is just the numerators. We already know that our denominators are all equal. Now I'm going to choose convenient x values to zero out these terms so I can solve for a and b. Let's start with, we're going to let x equal 8. And if I do that, I get 12a plus 0 equal to 2. Notice this time I don't have an x over here on the right side, so there's nowhere to plug in that 8. We're just plugging it in over on the left. And if I divide both sides by 12, then a is equal to 1 over 6. 2 over 12, which reduces to 1 over 6. The other convenient value would be negative 4. Negative 4 is going to zero out my a term. So I get negative 12b. Oh, sorry, I didn't put my 0. And you don't have to show the 0, but I'm just showing we zeroed out that first term. Minus 12b is equal to 2. And therefore, b equals negative 2 over 12, or negative 1/6. So now I'm going to rewrite my expression. 1/6 over x minus 8 minus 1/6 over x plus 4 dx. Rewriting my original rational expression using this form that I set up, and it becomes this, because my a is 1/6 and my b is negative 1/6. And so now we're ready to integrate. It might be helpful to pull that 1/6 out in front since they both have 1/6. This might look a little nicer to you for integration. So I'm going to have 1/6 times, again, it's kind of that u sub that we don't really have to write out because the du is equal to the dx. So we're going to think about this as 1 over u. The derivative, the integral would be natural log of u. So natural log of the absolute value, the absolute value of u, the absolute value of x minus 8, minus natural log of the absolute value of x plus 4, plus c. And let me take this opportunity just to remind you about log properties, because often when we see these problems in the AP test, the answers will be written in a different form using log properties. Remember that if you are subtracting logs like this, we can rewrite that as x minus 8 divided by x plus 4, still both an absolute value. We could also make this 1/6 an exponent. Or, remember, if we have a fraction exponent, that could be written as a root. This would be the 6th root of the natural log of x minus 8 over x plus 4. Both still an absolute value, plus c. Now, as far as working these problems out, I'm fine if we stop at this first step. Just know that on multiple choice, your answer most likely would look like one of these two. I don't think College Board doesn't often go this far, but I would expect the multiple choice answers to resemble one of these two simplifications.